Today, we're building a powerful real-time state of charge SOC monitor for your batteries. Whether using LiFePO4, lead acid, AGM, or gel battery chemistries, this setup will give you accurate insights into your battery's charge level in real time. But that's not all. This monitor also includes safety features like current and temperature monitoring, with alerts to notify you of any potential issues, from preventing overheating to catching excessive current draw before it causes damage. This system will help you keep your battery safe and running efficiently. Plus, with the ability to remotely monitor your battery status, you can easily check your state of charge from ashore or at home, ensuring that you're always in control of your battery's performance. For example, I have a LiFePO4 battery with a built-in Bluetooth BMS that includes a state of charge monitor, but I found that it's not always as accurate as I need it to be. With this custom SOC monitor, you have the flexibility to configure it based on your specific setup, giving you much better visibility into actually what's happening with your battery. Plus, you can make adjustments over time to ensure the most accurate readings possible. Now, you might be familiar with the traditional method of using a shunt to measure current. Personally, I prefer using a Hall sensor as it's so much easier to retrofit. Just clip it over the wire without the needing to cut anything. In contrast, using a shunt requires cutting the existing cable, placing the shunt in line, which means adding new cable lugs, making extra connections, and potentially dealing with a more complex installation. If you prefer using a shunt instead of a Hall sensor, don't worry. The SOC code and configuration in this video will still work. The overall setup stays the same, but you need a slightly different ESP home configuration to account for the shunt's input instead of the Hall sensor. For this project, we'll again be using the versatile ESP32. It will serve as a central hub, wirelessly transmitting data from the battery back to our smart boat system. If you're not familiar with the ESP32, don't worry. I have a separate video guide that walks you through the setup process step by step. We've worked with the INA219 before in previous projects, but for this build, we're going to use its big brother, the INA226, which allows us to handle higher voltages and makes it ideal for 24-volt battery setups as well. Along with the Hall current sensor, this combination provides precise data to monitor both voltage and current, key metrics in calculating your battery's state of charge. One of the additional features we can include is monitoring the battery temperature using the same method I demonstrated in my engine temperature video. To keep this video simple, I'm not going to show how to add a temperature sensor again, but you can watch my dedicated video on that topic. The great thing is you can use the same ESP32 that monitors your battery to also handle the temperature sensor. By adding a temperature sensor, we can track the battery's heat levels, which is crucial for maintaining safety. You'll be able to set up alerts to notify you if your battery temperature gets too high, protecting your battery from overheating and potential damage. We can also configure alerts for situations like sustained high currents that could indicate a problem. For example, if your system is drawing more current than expected for an extended period, you'll get a notification giving you the ability to take action before something goes wrong. This is especially important when working with lithium batteries because they store a significant amount of energy and are capable of discharging their energy really quickly. If there's an issue, like a short circuit or faulty equipment, it can result in a massive current discharge that could lead to overheating, damage to equipment, or even more serious consequences like fires. By setting up real-time monitoring and alerts, you can recognize these high current events before they become dangerous. The system will notify you immediately if the current exceeds a safe threshold for an extended period, allowing you to shut down the system or take preventative action. Of course, the battery should be adequately fused to provide a first line of protection, but this combination of hardware fusing and software monitoring ensures maximum safety of your system. If you have virtual switches set up, You can be more sophisticated by also switching off devices during alert situations. To make it easy to track your battery status, I've written some custom ESP home code and created a Home Assistant dashboard that will let you fine-tune your SOC monitor directly from the dashboard. On this dashboard, you can easily customize key settings for your SOC monitor. First, you can set the initial state of charge, allowing you to define the starting percentage and reset it whenever you need to recalibrate your system. Next, under battery capacity, you'll input your battery's rated capacity in amp hours, ensure accurate tracking of its charge. You can also adjust max and min voltage values, which define the voltage range for your battery. This helps the system automatically set your state of charge to 100% when the battery reaches max voltage and to 0% when it reaches minimum voltage, helping you fine-tune your monitor over time. Finally, you can tweak the charging and discharging efficiency settings to match your battery specification, making your SOC calculations even more precise. For LiFePO4 batteries, a typical charging efficiency is around 95%, while discharging efficiency is generally higher, around 98%. For AGM batteries, the charging efficiency is slightly lower, usually around 85%, while the discharging efficiency is around 90%. But these degrade substantially as the AGM or lead acid battery ages, so you might need to adjust them every year. This monitor will give you live feedback on your battery's health, as well as historical data you can use to understand your battery's behavior over time. First, I'll show you how to connect all the components: the ESP32, the Hall sensor, and the INA226 voltage sensor, so you can easily follow along and get everything set up. After that, I'll walk you through how to configure all of this in Home Assistant to ensure you have real-time access to your battery metrics wherever you are. And if you haven't yet set up your boat as a smart boat, I've also created a tutorial playlist that will guide you through the entire process. So let's get started. Here we have the Hall sensor. I have a 200 amp model, but you can get it all the way down to 20 amps. So obtain the one that's closer to your maximum charge or discharge rate that you expect. It's quite a good build on these. I was quite surprised. It has an arrow, so I like to orientate the arrows so it points in direction into the battery. So the positive charge, I'll have it going in, and the negative charge will be going out. Although it doesn't really matter, you can actually go the other way around, and just when you do the calibration, you can flip it. It has a simple clip, unclip it, so it's really easy to install. Sometimes it comes with 4 wires, but you only need the 3. You need the red, black, and the yellow. There's an extra 4th one, but you can ignore that. So we're going to connect it to the 3 volts, the 32 pin, and the ground on the ESP32 on the breakout board. So the first one is the 3 volts. So it's going to be powered from 3 volts from the ESP32. And then the ground, which goes into the ground terminal of the ESP32. And the yellow, which is the data cable, which is we're going to connect to pin 32. So the V out, it's called. So now we need to connect the INA226. It's very much the same as the INA219. It has the I2C pins and then the VIN plus pin to connect to the battery for the voltage sensing. So I'll just quickly connect the DuPont connectors. Pretty easy with these DuPont connectors. Red for the 3 volts, black for the ground, the yellow for the SCL, which is I2C SCL, and then the brown for the I2C SDA. So that is all the communications between the ESP32, and then this red cable is going to be connected to our battery. Will be our sense cable. So this is how it's going to sense how many volts we have on our battery. Just connected to the ESP32. The first one is the ground. Now it's quite important for the voltage sensor to work, to give you the correct voltage, that we use the same ground for the ESP32 that we have for the battery. So we have the same 0 volt reference. If you don't use the same ground, I mean, it's most likely the same, but if you don't exactly the same, the voltage might be a little bit out. I'll just connect the two data cables, the yellow SCL and the brown STA. Now the INA226 will also be powered by 3 volts, so we have to share this 3 volt terminal with the Hall sensor. So I'll just connect to the same terminal. And there we have it. So the red cable goes to the battery and everything else, and the Hall sensor clips over to the main charge discharge cable to the battery. Now to power this, it's better off to power it with a adapter. Like I have 12-volt batteries, so a 12-volt to 5-volt adapter like this one. The black and red go to the battery, and the yellow black go to the ESP32. The black goes to the ground, and the yellow goes to the 5-volt terminal of your ESP32. I won't connect it because there's so many different adapters out there with different colors. And in between your battery and your adapter, you should fuse it. Here I have a simple blade fuse, a mini blade fuse. I think it's 1 or 2 amps I have here. You can probably get away with half an amp. So we put this between the battery and the 12-volt to 5-volt adapter. So here we are in Home Assistant on the ESP Home dashboard. Now to start this project, you need to have an ESP32 that's been provisioned. So if you haven't done this before, watch this video of mine, which shows you how to provision an ESP32. So we're going to start off with this blank one. I've got one created called Battery ESP32. So if you have a look inside, it hasn't got much to it. So it's just got the name, Wi-Fi. I'm using a static IP address, but you don't need to. And the logger level and the OTA. So this is pretty much the standard basic starter ESP32 YAML you need to have. It would be helpful if you keep it the same name as mine, battery-ESP32. Well, it doesn't matter too much, but when it comes to the dashboard assumes this name. So if you have a different name, you just have to do some editing in the dashboard YAML. Otherwise, if you keep it this name, you should just copy and paste the dashboard I provide you. Now, like with my other projects, I provided you some code on my web page. So if you go to my website and under code, under SOC battery monitor YAML, if you scroll down, there's a download ESP32 YAML. So just click on that and download it, and then just copy the contents and put it at the very end of this base YAML. So paste it in there. I'll just go through this. So it starts with this time platform. You need to have that for this to work, for the statistics and Home Assistant to work. Now there's a lot of code I've written, which is I've abstracted from here and I put it onto my GitHub page. Here's the link to it. So that this will include that code into this ESP YAML. If you want to go have a look at it, you can just go to this URL and scroll down, and here we have. It's quite a bit of code. It's about over 300 lines of code, and it's relatively involved, but it works quite well. And it's involved because I've had to integrate it into the Home Assistant environment for how energy and batteries are used. So it has all the statistical entities, etc., etc. But I won't explain how it all works. But you can, if you like. If you want to change this, you just copy it into your YAML and then change it if you're so inclined. So if we go back, so I have this is the GitHub. Now I have the I2C, which is what we're going to connect to the INA226 sensor. So this is just to find the pins 22 and 21 that's how we connected it. And here in the sensor section, we have the INA226 defined. Base configuration for ESP Home for INA226. And we're just going to call it battery voltage. Now the Hall sensor is the next one. It's the analog to digital converter. It uses that platform. And here we've connected to the pin 32, same as I showed you before. and we're calling this one battery current. Now this takes samples from the Hall sensor. Now to get this all working, we need to calibrate it. So we need to calibrate the range, and this range is from 0 volts up to 3 volts potentially, what this ADC platform will return. So we then have to calibrate the numbers it returns to the actual current. So it's good to take 3 or 4 readings. I've just put a nothing calibration here, so 0, 0, 1 to 1. Okay, firstly we'll save this, and then we'll just hop out as I normally do. We'll validate it. Okay, and then install it wirelessly OTA over the air. I'll speed this up. Okay, it's successfully uploaded. So now let's go create a dashboard. So we go to settings, dashboards, add a dashboard, new dashboard from scratch. We'll battery monitor, there's a battery icon. Create. Okay, so I've created some YAML code for the dashboard that you can start off with. Again, it's on my web page, and it's on the second button here, which is the same page, the SOC battery monitor YAML. So the download dashboard YAML. So if you just download that, and copy it all, and then on this dashboard, if you go to the top here, the pencil, and again the raw configuration editor, and just select it all here and paste it in. It's a basic YAML and you can change it, but it's a good starting place. You might want to split it up. So, but just if you here you have a look, all the sensor names are here, battery charging power, but they're prefixed with the battery underscore ESP32. So if you called your ESP32 and ESP home something else, you need to change all these. I tried to look at a general way to do this, but unless you can tell me how, I couldn't figure it out. So you just have to put this into an editor and do a replace all battery ESP32 to whatever you want to call it and put it in. It's not too much work. So let's just save that. Exit. Done. So I have mine connected, my LiFePO4 battery. So that's what it looks like. You have the state of charge gauge at the top here, tells you if it's charging or discharging in watts, and the current in amps, and the current voltage. And then down here we have the configuration. So you can set your manual state of charge, capacity, min and max voltage, charging efficiency. So maybe if in real life you can split these into two dashboards, one for the display and one for the configuration. But I'll leave that to you. So what we need to do at the moment, the YAML on the ESP home, this hasn't been calibrated, so it's only returning values from 0 to 3. Now what we need to do is calibrate a few values with a known current. Now the easiest is if you use like a multimeter with a clamp, or if you have some other gauge to tell what actual amps are coming in and out of your battery, because we need to calibrate this. So if we go back to the ESP home, down the bottom here, at the moment I have 0 to 0, 1 to 1. But on my boat, which I've already calibrated, I have these settings. So I use my multimeter, which has a clamp meter, but there are other ways you do this. So I had everything disconnected, and 0 was coming in, and it was returning 1.68 on the dashboard. And then at 34 amps, it was returning 1.78, 55, 1.85, and when it's discharging, -3 discharge was 1.67. And if you get like 2 or 3 or 4 points, then it's pretty much a linear graph, and Home Assistant ESP Home will calibrate the values for you. So once you have this calibrated with the values in here, again, just save. Let's install it. Okay, it's uploaded. It's successful. So if we then go back and have a look at our dashboard now. Okay, you can see now it's actually discharging. Have a discharge of 137 watts, which is like 10 amps. So a negative discharge, a negative current means it's discharging. For example, so if you wanted to then say set the state of charge, say it's not 89, say it's 75%. You can just do that and it'll update it straight away, and we'll start calculating based on that it's 75% at the moment. Again, I've got my min and max voltage set up for lithium, and also the charging and discharging efficiencies. But you can change any of these whenever you like. So for alerts, I'll just show you a really basic standard alert I've set up for this. So when the battery is high current, so basically when the battery current entity is below negative 100, so a negative current is discharging. I'm not too worried about charging, but I'm a bit worried about if the battery is discharging at a high amps. And I've set for 10 seconds. You can change this 10 seconds, 5 seconds, depends on what your load is. I shouldn't have anything more than 100 amp discharge for more than a few seconds on my boat. So it's less than minus 100, and I have 10 seconds, and then I just have the action to turn on the alarm and send a WhatsApp. And you can do the same for the battery temperature. If you put the battery temperature one wire sensor on there, and then again, as I said in the introduction, you can get much more sophisticated with the actions, and the actions can be more than just turning on alarms and sending WhatsApps. You can actually then, if you have virtual switches, you can turn off some of your devices via virtual switches. So one of the extras about the GitHub ESP home code I wrote for this SOC monitor is that I've created a couple of entities which are useful for the energy management in Home Assistant. So if you go to the energy dashboard, you can see now that there's energy coming in and out of the battery, and you can also see it on the energy usage graph. Now I've done that by, if you go to the energy configuration, here you have the home battery storage, and this is where you put the two entities I've created in the GitHub code. It's battery energy in and battery energy out. Of course, it's prefixed with whatever you called your ESP32. So from now on, you'll be able to look at the statistics daily and weekly and monthly of your energy usage within Home Assistant. It's very useful. Thank you for joining me today in exploring the incredible world of smart boating. If you found this video helpful and informative, I would appreciate if you hit the like button below. And if you'd like to stay updated with more exciting content on boating and technology, consider subscribing to my channel by clicking the subscribe button. Your support means a lot and helps me create more valuable videos like this. Until next time, hasta luego.